Well, hello. Today we are going to be talking about section 7.2 in our textbook, which is hypothesis testing for the mean when we know the standard deviation. And that's important because when we don't know it, we're going to have to do something a little bit different. Okay? So we're going to be using p-values to make decisions. And we're going to be comparing those p-values, that's the probabilities. We're going to be comparing that with our alpha. Now our alpha is what level we are going to be testing at. Remember we talked about alpha levels of like 0.01 or 0.05 or 0.10. And in a way you could think of that as kind of like being, 0.01 is kind of like being 99% confident that you're right. Okay, that's kind of how a good way to think about it. Now, what a p-value is, that's the likelihood of getting a value as extreme as you got, given that the null hypothesis is true. So if you get a p-value of like 0.03, then the likelihood of you getting, the likelihood of your data being as extreme as it was, if the null hypothesis is true, is only about a 3% chance of that happening. Okay, and so in a lot of places, if your alpha was 0.05 and you got a p of 0.03, then you would reject the null. If your p-value is larger than the alpha, then you fail to reject the null. Okay, so let's go ahead and take a look at just what this might look like, a couple pictures, so to speak. So if your alternative hypothesis contains a less than sign, then your rejection area will be on the low end. If you end up getting a z-score that's down past whatever this number comes out to be, and this is based on what alpha you choose, okay, then your rejection region would be below that. If your alternative hypothesis contains a greater than symbol, then you're looking to get a value that's up higher than that. Okay, and then of course we also talked before about the not equal to. You make a claim that John eats 5 hot dogs every day. Well, then the alternative is that he does not eat 5 hot dogs. And so then what happens is you actually split that up between the two. And notice that this says 1/2 p. Right? Well, remember that your rejection region is split in half. Okay, because you don't necessarily have a direction. You don't have information that leads you to believe that it's more or that it's less. You're just checking that it's different. Okay, so let's go ahead and take a look at a few problems from your homework that you might run into. Number 10 here. Find the p-value for the hypothesized test with the standardized test statistic z, and then decide whether to reject the null for the level of significance A, alpha. So let's say we run our test. We collect some data, we do the proper testing that we're doing, and we end up getting a z-score of -1.55. And if we're testing at the alpha 0.05 level, what we want to know is, does that z-score end up down here in the rejection region? Remember, our rejection region in this case will be somewhere down in here, and this area is alpha 0.05. We want to know, where does z fall? If z falls down in here somewhere, if this is where z is, then so we'll put like this, 1.55 negative question mark. If that's true, then we would reject the null because it's down, this would be down below alpha 0.05. But if instead it ended up right here, then our z-score would actually be above that. Okay, so let's go ahead and let's check. I'm going to set this right down here for now. Let's go ahead and to our graphing calculator. You could, of course, use a z-table and use your p-score, p-value 0.05, and find a z-score for that. But let's go ahead and use our calculator, since I think that's what most of you would want to do anyways. And I think it's maybe even easier to show here online. So let's go into what we want to know is where this falls. Right? So let's go into distributions, and we're going to go down to normal CDF. Okay, so inside normal CDF, now a lot of you have the little bit nicer ones, but this one is just going to go min, max, mu, standard deviation. So we want to know what area is to the left of negative 1.55 in a standard normal curve. So I'm just going to go ahead and put negative 99999, just a bunch of nines. And then we'll do all the way up to negative 1.55. Min, max, mu is 0, and then standard deviation is 1. Okay, this gets us 0.06. In other words, our p-value for this would be p equals about 0.06. Now, that's not less than alpha. In fact, like if we were to come back up here and we were to put this up here, it would actually kind of be somewhere in here. So this does not fall into our rejection region. We would not reject the null in this case. Okay, so this is a left-tailed test. Our rejection region was over here on the left. So in this case, let's make sure that we actually answer this. And what I would say here is, no, we fail to reject the null. Okay, our p-value ended up not being less than alpha 05. We only reject if it would have been less. Okay, so let's go ahead and look at another example here. A right-tailed test. And this time we're testing at the alpha 0.10. Okay, so this means that we are 10% likely to end up making a type 1 error. Okay, so 10% of the time we'll make a type 1 error, meaning we reject the null when we shouldn't. Okay, when the null hypothesis is true, but our data ends up leading us to believe that it's not. So what this might look like, in other words, this time our rejection region is right-tailed, and you can see it's actually a little bit bigger. This time our rejection region is that. And we want to know, where does z equal 1.23, where does that fall? Okay, so let's go back to our, is z somewhere over in here? There's 1.23 over in here. There's a couple ways to do this, but we'll just go back into our TI calculator. We'll go into distributions again. And this time, go down to normal CDF. And we're going to put in 1.23 as the minimum. I'll just put in a really large number for the maximum. And again, we're still going to use a mean of 0 and a standard deviation of 1. Now this gets us the area that is to the right of 1.23. And you can see that we get 0.109. Because our p-value was once again larger than our alpha, right? Our p was equal to 0.109 and our alpha was equal to 0.10. So because that was true, look, p is greater than alpha, which means that once again we are going to fail to reject the null. Okay, so once again we fail to reject the null. Lastly, we were going to run a two-tailed test, and this time we want to know if we have a z-score of 1.95 and we're running a test at 0.08. We want to know, will that reject it or not? So if we are running a two-tailed test, and that means that the area in these two tails is a total of 8%, which means that, or 0.08, which means that each individual area is 0.04. So now we want to see where 1.95 is. Now, to be honest, you can check either the lower or the upper half. We'll use since we're using the positive 1.95, we'll go ahead and check that. But if this is 0, I want to know if 1.95 falls down here, then you would reject. If 1.95 falls in here, we haven't gotten to the rejection region. Okay, so All right, let's go ahead and back to our TI calculator. And I'm going to show you two different ways to do this on the TI. Okay, so the first one, we'll kind of do it like what we were doing. Let's go into distributions, and we'll go down, we'll do normal CDF, just like we were a little bit ago. And this time we're going to go from, why don't we go from negative 1.95 up to positive 1.95. Let's see. One 1.95. Okay, and then we'll still use the mu of 0, standard deviation 1. Okay, so what this tells us is from negative 1.95 to positive 1.95 is about 95% of the data. And what that tells us is that in this region here, let me erase some of this. If I were going to graph a normal distribution, so here's what that looks like. If I go from a z-score of negative 1.95 to positive 1.95, then this area right in here is about 95%, which means that only 5% is left for the two of these to share, which means this is about 0.025 and this is about 0.025. Now I rounded it, but what that shows you is that yes, this z-score is definitely down in the rejection region. It would be down in here, okay, because it's actually 0.025. All right, now I also said let's go ahead and do this another way. If we can figure out exactly what z-score this is, then we'll know whether 1.95 is past that. Okay, so all we got to do is this time we'll use the inverse norm on the calculator. So again, this is just another way of doing this. I'm going to go into distributions again. We'll go down here to inverse norm, and I'm just going to use 0.96. That's because I'm going to go all the way up to this spot right over in here, and I want to see what this z-score is, what 96% of the area would be. This z-score is actually 1.75. If the z-score is 1.75, okay, so I know this part right here has a z-score of 1.75, then if I want to know 1.95, then clearly 1.95 falls into our rejection region because it's past that. So in this case, this is the first time that we actually get to reject the null. When we run a z-test for the mean, you can find your standardized test statistic just by doing our x bar minus mu over sigma divided by radical n. Remember, this is the standard deviation of the sampling distribution. It's also known as the standard error. Okay, so the larger your sample size, then you're going to be dividing this down, and you're going to get a more accurate result. You have to have a couple conditions before we can do a z-test, though. Either so the sample has to be random. If you're selecting a sample that's not random, then this doesn't really work. If you're using a convenience sample, you're doing something else, we just don't do that. Okay, not a lot you can tell if you're not doing some type of a random sample. Now, notice this says at least one of the following must be true, and this isn't different than what we've done before, but the population either has to be normally distributed. In the past, we looked at that, or our sample size is going to be larger than 30. If we have larger than 30, we looked at how the sampling distribution of even skewed sample or of skewed populations, the sampling distribution is approximately normal when you have large sample sizes. Okay, so let's go ahead and look at a couple more problems that you'll run into on your homework. We're going to test the claim about the population mean at the level of significance alpha. We're going to assume the population is normally distributed. Now, that's important to do because you can see right away that when we look down here, we see that our sample size is only 26, so it doesn't meet that 30 threshold. So we already have to make that assumption if we want to move forward. Okay, so let's go ahead and start thinking about what we're going to do here. Our claim is that mu is greater than or equal to 1475. So our null hypothesis will be mu greater than or equal to 1475. And then our alternative is going to be the exact opposite of that, that mu is less than 1475. Now, in our book, we just kind of go by this default of whatever the equality, whichever one is the equality, that's going to go in the null hypothesis, whichever one has the equal sign, so to speak. Okay, so let's go ahead now and notice that we're testing at the alpha equals 0.07. So let's go to our calculator and we're going to put this in the calculator. Okay, so I'm going to not go to distributions this time, rather I'm going to go to statistics, so go hit stat, arrow over to tests, and we're going to do a z-test. Now, even though we're talking about a mean, we're doing a z-test because we have a known standard deviation. We see that right here. They give us the population standard deviation. Wow, I just said pop like I'm from Boston. I am not from Boston. So the population standard deviation was given, and that's why we're using a z-test. You might remember ZAPTAX that we've talked about before. Z's are for P's, and T's are for X bars, right? But this is whenever we don't, we use t-test when we don't know the standard deviation, and we'll look at some examples of that in the next lesson. But let's get back to our calculator here, and we're going to use a z-test. So in tests, just hit number 1. We're going to make sure this is over on stats, so go over there, hit enter, because we are given our summary statistics. And now we're just going to put in 1475 is the null hypothesis. Okay. Our standard deviation is 29. The sample mean is 1468. And then our sample size is 26. Okay. Now the alternative is that it's actually less than that. So our claim is that it's greater than or equal to 1475, and the alternative then would be that it is less than this. So let's go ahead and calculate. Whoops. So used to just hitting enter on my other calculator. Okay. We've got a p-value of 0.109. Oops. P equals 0.109. So just as a reminder here, you can see that what we ended up with was p was greater than alpha, and therefore we fail to reject. Fail to reject the null. Okay. Now let's go back over here and check this two-way table. Remember, in this case, our claim was the null, and we ended up failing to reject the null. So what we would say is there is not enough evidence to reject the claim, right? But there's also not really evidence supporting this claim either. And really, if you think about this, look, we took, I don't know what the context is here, but we took a sample and we got a mean of 1468 in our sample. So it wouldn't make sense to say, oh, let's now accept the claim that the mean is actually 1475 or larger. We really don't have any evidence for supporting that. And that's why we are careful with our language here, and we just say there's not enough evidence to reject the claim. All right, let's go ahead and kind of explore that, and that's ultimately what you would write down here, because it did say to interpret, so we would say there is not enough evidence at the 7% level to support the claim or reject the claim. You know, but let's go ahead and explore that just a little bit more, because I think not everybody understands why we don't just accept the null hypothesis to be true in this case. So I'm going to do something that's maybe has a little more context to if you're here in Phoenix like I am, and it's been hot recently. I can say that almost any time of the year, and it feels right, even if you're watching this at Christmas time. It's like, yeah, it's hot outside. So let's say, here's an example why we don't just accept the null. Okay, so consider that the average air temperature, and I make the claim, the average air temperature is 110 degrees. Okay, that's my claim. So if I let that be my claim, and I say H null is 110 degrees, then the alternative would be that, you know what, it's not actually 110 degrees. Okay, and then I'm going to do something. This actually goes to t-tests, which is a future lesson, but I think you'll still get the idea. If I go ahead and I put those in my my list, so I took some temperatures. I have 102, 106, and 108. And I put those in here. Again, this is more so for a future lesson, and I go over to tests, and this time I would actually be doing a t-test because I don't know the true standard deviation, but it's very, very similar. Oh, I'm going to use data instead. So 110 degrees, use that, and I will select not equal to. So what I end up getting, oh, you know what I didn't state was what level of significance I wanted to test at. Let's say I wanted to test at the alpha 05 level. Okay. So if that's the level I want to test at, you can see I end up getting a p-score of 0.118. P equals 0.118. Now, what we know is that alpha ends up being less than p, right? This is larger. We only reject when our p is lower than alpha. So in this case, I fail to reject. I don't have enough evidence in order to reject the null. I fail to reject. Now consider that language though, because I don't just accept the temperature is 110, because that doesn't make sense. Look, all of my data here says 102, 106, 108. My gut feeling says it's not 110. All of my data says it's not 110, right? And so I don't have evidence to support this claim. I don't have evidence for that. All I can do is fail to reject, and I can say, you know what, I can't prove that it's not 110, but I can't prove that it is. It's the difference in a jury trial between innocent and not guilty. In a jury trial, you are never found innocent. Okay? You're always found to be not guilty, like there's not enough evidence to convict you. But at the same time, we don't just declare people innocent. So in this case, there's not evidence supporting this. All I can do is fail to reject. Now let's say that we take a couple more days of measurements, okay? And let's say we have a couple more days of measurements where we get another 106 degree and another 105 degree and another 107 degree day. Okay, so now you'll notice that we're getting a few more samples. Oh, no one would probably argue that 102, 106, and 108 wouldn't come from a normally distributed population. I just want to say that, because obviously our sample size is less than 30. Okay, but I did want to mention that. Now, if we go back in here to tests now and we do the same thing, data, you can see that what's going to happen here, because we took some more data, we have a tighter error, if you will, and our p-value is now very, very tiny, right? In a case like this, where we added a few more days worth of information, at this point, Now we can say that with a p-value of 0.003, now we finally get to reject the null. We have information that says the true temperature is not 110 degrees. So we can finally reject this. We like, reject the null, get it out of here. We have evidence to support this. Or you might say we have evidence to reject the claim that the air temperature is 110 degrees. Now I know that went on for a little bit, but I hope that that kind of makes sense why we don't just accept the null. Okay, now you can reword some things at times depending on whether you want to take a stance on something, if you're working for someone. We talked about that a little bit in the previous lesson, where you can try to make it so that your claim is always in the alternative section, and that way you can prove a claim true in that way. Okay, but that's not what this is. I just wanted to go back and show you why we say fail to reject the null. There is not evidence to reject the claim that mu is greater than 1475, and there's really not evidence to support it either. Okay. I want to go back and revisit this and do this one by hand real quick, just because it's a good idea to always do the first one by hand. And remember what our formula was z, our critical value, was equal to x bar minus mu over the standard error then, which was sigma over the square root of n. So when we put some numbers in for this, we get 1468, go up here, minus 1475 divided by, and then this would be 29 over square root of 26. Again, this is how we would do it by hand. You put all that into your calculator very carefully, and then you end up getting z is equal to negative 1.2308. So that's our critical value. Then what we would do is we would use our normal CDF. So we'll go into here, we'll go to distributions, normal CDF, and this time we want to go negative 99999 all the way up to negative 1.2308, because we're looking to see how much area there is in that lower left-hand tail. And if that area is less than 0.07, then we'll reject. Okay, comma 0, comma 1. And oh, we get 10.09. Now that's the same thing we found over here with our P, and then ultimately we end up fail to reject. Okay, so it's still the same thing. I just kind of wanted to show you how you find that z-score by hand in case I ask you to do that on a quiz or something. Also, it's a little more work that you can show. The calculator, just plugging it into that z-test goes pretty quickly though. All right, let's go ahead and let's check out number 30 from your textbook. We're given some information. We're told the claim is that the true mean is less than 22,500. And then we have an alpha of 0.01, our standard deviation of 1,200, and then our sample statistics. The sample mean is 23,500, and our sample size is 45. So right away, see how this one has the equal to it, so we'll make that the null, is that the true mean is less than or equal to 22,500. And again, this is our claim. And then the alternative is that the true mean, that's not true, right? That the mean must be greater than 22,500. A little comma there. Okay, and we want to test this at the alpha equals 0.01 level. Now, right away, I do have some evidence here that kind of suggests this might not be true, right? So that makes sense to go ahead and run this test. They're claiming that it's less than 22,500, and it seems to me that my evidence is going to end up probably rejecting that. I don't know. Let's see if it fits. So let's go to our calculator. We're going to do this one just all on the calculator. We go into stat, tests. We're going to do a z-test. Again, I realize we're talking about mean, but because we know the standard deviation, we can use this. Okay, so I'm going to make sure it's on summary statistics. And we'll go down. Our hypothesis is 22,500. We're told that this is 1,200 for the population standard deviation. And then we took a sample and we had 23,500. Our sample size was 45. And then the alternative is that we are actually greater than the null. So let's go ahead and calculate that. You can see we get this. Now, at first glance, you might look at this and say, wait a minute, 1.372, p equals 1.372. Oh, that's greater than alpha. Okay, well, I failed to reject. Oh, you got to look closer, though. Look, it's 1.1372 e to the negative 8. That's probably important. This is scientific notation, right? This means like times 10 to the negative 8. So really, this is 0.0000006 01372. Okay, 1, 2, 3, 4, 5, 6, 7, 8. Yep. Okay, that's what our p-value is. That's teeny, teeny, tiny. So definitely p is less than alpha. And when p is less than alpha, that's when we get to reject. Reject the null. Right? We finally get to do something. We get to reject the null. We get to say, get this out of here. Okay? So I would then say, for my interpretation, I would say there is evidence at the 1% level level of significance to reject this claim. Okay, sometimes we can't support it, but you know what, this time they made the claim. They said, hey, our claim, the claim is that the mean is less than 22,500. And you know what, we can definitely say no. At the alpha 01 level, that's a really, really strong level. We can be really, really sure of ourselves that this claim is wrong. That's a lie. The mean is not less than 22,500. Okay, we can feel pretty confident about that. Let's look at some other types of problems. We've already kind of done some kind of like this, but I just want to make sure you can see exactly what we're looking for here in a problem like this from your text. So find the critical values in the rejection region for the type of z-test with the level of significance alpha, then graph your answer. Include a graph, right? So a left-tailed test with an alpha of 0.9. What that's going to look like is ultimately we want to have a left tail, okay, that's this over here, with this to be 0.9, and we just want to know what this is, what that z critical value is. And the easiest way to do this, I mean, you could go to a chart, but I don't think many of you are using tables and charts. You could go to chart and find a p-value 0.09. But on your calculator, do you remember how to find a z-score for a given p value? Well, that's your inverse norm. So that's under distributions. And we're going to go down here to inverse norm. I'm just going to use 0.09. And you can actually just use just 0.09. You don't have to put in the others because it will automatically do a standard normal curve for you. You could put in the mean and standard deviation here and you'll still get the same answer, but ultimately what we find is we get negative 1.341. If we went to 2 decimals, it'd be negative 1.34. So there's our z-score that would be the cutoff value if we had an alpha of 0.09. So what we would say then is our critical value, like z naught, if you will, would be negative 1.34. Put a naught there. And then the rejection would be any time that you get a z that's less than negative 1.34. So if you get anything less than negative 1.34, then you would reject. If you don't get something less than negative 1.34, then you fail to reject. Number 24, this time we're doing a two-tailed test. Let's go ahead and get ourselves a little more room here. And what we want to do, again, we've already kind of done this, but if we have 12%, then that means that there's a total of 12%. Okay, that's the total amount, which means this part is 0.06 and this part is also 0.06. And so what we want to find is this z-score right here. So we'll go back to our calculator, and we're going to once again go to inverseNorm. That's in your distributions. We'll go down to inverseNorm, and think about what we're going to put in this time. If I want to find this value right here, I don't put in 0.12. We'll put in 0.06. And that gets me a z-score of negative 1.55. Now, because this is symmetric, I know that the top part is a positive 1.55 as well. So this is 1.55 negative, and this one would be positive 1.55. Okay, so our z naught, if you will, would be negative 1.55 and positive 1.55. And then our, so that's our critical value. And then our rejection region is going to be if z is less than negative 1.55 or if z is greater than positive 1.55. If you get a value up here to the right of it, then that would also be a rejection region. All right, let's look at one more problem and then we're going to be done for today. Identify the claim, okay, and state the null and the alternative. Find the test statistic z. Find the corresponding probability. Find your p-value. Decide whether to reject or fail to reject, and then interpret. Okay, so we've got to do all those things here, and I'm going to make a little more room here. The manufacturer of a sprinkler system designed for fire protection claims that the average acting temperature is at least 135. Okay, when I see at least, that makes me think that we're talking about greater than or equal to. To test this claim, you select 32 sprinklers, and you find that the mean temperature is 133. Ooh, that makes me think that, you know, we might be able to prove this guy wrong. Standard deviation is 3.3. We know that from I don't know, lots and lots of samples, I guess. So we're going to assume that that's the population standard deviation. And then we're testing this at the 0.10 level. So right away, we are going to list our hypotheses and then our claim. So the null hypothesis is that the mean is greater than or equal to 135 degrees Fahrenheit. That leaves the alternative to be that mu is less than 135 degrees Fahrenheit. And then it says he claims that the average acting temperature is 135. That makes this one to be our claim. This, of course, is our part A. Our part B then says to find the z-score. And let's go back and do one by hand, and then we'll verify it on the calculator. But that's just going to be 133 minus 135 divided by 3.3 over radical 32. When you put this in the calculator, make sure you put this part in parentheses, and then you'll be set. You should get a z-score equal to negative 3.428. That's what I have here. Okay, So there we have that. Then you could go through and do your normal distribution and find what that is. So let's go ahead and find our p-value here. So this is kind of doing it all. I don't want to call exactly by hand because we are using a calculator. But what we want to know is we want to know how much area is to the left of this in a standard normal curve. So I'll go here to distributions. Got to go to normalcdf, and we'll use negative 99999, comma, negative 3.428, comma 0, comma 1. There we go. Now you can see it has this E here again. That's scientific notation, and that's going to mean then that our P is equal to about 0.0003. Now, in part D here, what we would say is, you know what, P is less than alpha, because we're testing at the 0.10 level. In this case, we reject the null. Okay, so we reject the null. In this case, we will say this. We'll say there is evidence at the 10% level, and some people will just say at the alpha 0.10 level of significance. Significance. Sorry for my sloppy writing. You'd think I'd be better, but it's kind of difficult to write on this sometimes. To reject the manufacturer's claim. The average. Probably should have just wrote this out and paused it, and then you wouldn't have to listen to me read so slowly. Activating like that. Okay, so there is evidence at the 10% level of significance to reject the manufacturer's claim that the average activating temperature is at least 135 degrees. That means that we think the manufacturer is wrong. We think, you know, he says that the sprinklers don't go off until, on average, 135 degrees. We're saying shenanigans. We don't believe you. You need to go back and check some stuff. We have really strong evidence suggesting otherwise. We think they go off at a lower temperature. We reject your claim. We say, no, get that out of here. Therefore, this one must be true. Okay? All right. So I know we did a lot on the calculator. We talked about rejection regions. We talked about failing to reject and interpreting. Please make sure you check your answers in the back of the book. It's a great place to check answers. You can check them online as well. Good luck with this. We'll look at what to do whenever we don't know the standard deviation another day.